Okay, my sound is, or voice is clear. If there is some problem, you can inform to me. And in previous class of split lecturing myself, Professor Dr. Nizam was told from the Euler's equation that is considered only the two type of forces, that is pressure force and gravitational force. We have derived the Bernoulli's equation, okay, by integrating the Euler's equation, and from that is P upon rho plus V square upon 2 plus Gz. To multiply these, we have got P upon rho G plus V square by 2G plus Z is equal to constant. This equation is nothing but the Bernoulli's equation, and we write down all the values about the Bernoulli's equation. And also we have seen the limitations of Bernoulli's equation of theorem, and then the limitations also we have seen. So these limitations we have seen based on the assumptions made by on the Bernoulli's theorem. So these are the assumption, and based on that assumption we have seen the limitations. What are the limitations? Limitation is that the Bernoulli's theorem is not valid for anesthetic law. In gravitational flow, eddies and vortices are formed, and due to this, energy loss is there, which is not considered in Bernoulli's theorem. Loss due to friction or viscosity is also not taken into account because only two forces are considered. Theorem has considered only a flow in case of incompressible fluid. It means that rho is constant throughout. This theorem is not applicable for the fluid flowing along third path. Find bend their working energy due to the centrifugal force is not taken into account. In case of Bernoulli's theorem, no provision for separation of flow or flow where cavitation takes place. These already we have covered in lecture number 19. Now we will see today in lecture number 20, which is your lecture number 20. So in lecture number 20, we will try to cover today's 1410. So we will try to cover the total energy line, total energy line, that is TEL, and and total energy line TL. Because we are working too much today. Total energy line TL, and you will see the hydraulic grade line, hydraulic grade line, that is called as HGL. HGL. So for that you have to draw the figure. Draw the figure. Okay. So draw this figure. So I draw this figure with the upstream side. Okay. There's 1 5, then another 5, then we have the check valve, and then flow, free flow, and draw the bottom line. To understand this, draw the bottom line. First chapter, once again you are left. So this is, we will draw the bottom line. Okay. So I will go down. center of this pipe 1, and this is the upstream side. I will say show with the water level. Okay. And to draw this is nothing but your this line. So here again it will drop due to the chain. So this line is called as total energy line, and sometimes it is called as energy grade line, EGL also, energy grade line. And below that, we draw here, we draw once again that is dotted line. So draw here. This line is called as HGL. HGL, that is hydraulic grade line. That is called as HGL, hydraulic grade line. Require too much that. Okay. So all the lectures are recording. When you are joining and leaving the class, it is also recorded. Okay. So don't think that you are too smart. Okay. So HGL, if you write on the HGL, so HGL will be the this part is P upon rho E, and this part nothing but from the bottom it is called as Z. Okay. So if I will write down the HGL will be Z plus P upon rho G, and total energy part is added here. This is nothing but V square upon 2G. Okay. So total energy line if I write down, it will be P upon rho E plus V square upon 2G plus Z. So this is your HGL and TG. So this is nothing but the concept of using concept of first total energy line and second atomic grade. Okay. So this is nothing but your concept of. So this you can write down theoretically and then write down from the equation of your uh, Bernoulli's equation. So you know that I will write down. I will write down. So you know that I think so. You have drawn this figure. This figure is very important. This figure have to draw. Huh? Figure you have to draw. Minute कैसा what is time now? You are too late. This figure you have to draw. Okay. If I will write down here, you know the Bernoulli's equation. Uh, Bernoulli's equation that is P1 upon gamma P1 square upon 2G plus Z1 that is equal to P2 upon gamma plus V2 square upon 2G plus Z2 plus some HL, that is energy head loss or energy loss you can say. So I will give this equation number 1, and you know that what is the P upon gamma is the P upon unit weight, that is gamma work done by the pressure force, by the pressure force, okay, per unit weight. So gamma is unit weight per unit weight of fluid, of fluid, and it is also called as sometimes, it is also called as pressure head. It is also called as pressure head. So already we have drawn the equation from the equation, and V square upon 2G, nothing but the kinetic energy. V square upon 2G is the kinetic energy of the flow per unit weight of fluid, per unit weight of fluid. And it is also called as sometimes, it is also called as velocity head. It is also called as velocity head. And Z is nothing but, it is called as potential energy, potential energy, potential energy per unit weight, per unit weight, and it is also called as datum head or potential head. It is also called as potential head or datum head. So this from the Bernoulli's equation we know. So we know that the pipe flow problems are very important for engineers who design distribution system for water supply and waste disposal, drainage water and these are problems in which control volumes are extremely large ratio of length to width. Thus, the Bernoulli equation must be modified to account the energy losses that result from work done by the tangential stresses, that result from the work done by the tangential stresses. So we know that if you account that, so modified Bernoulli's equation, if you draw it down, H1 plus V1 square upon 2G is equal to H2 plus V2 square upon 2G plus the energy losses or head losses, that is HL. I will give the equation number 2. And we know the discharge is nothing but to the A1 V1 is equal to A2 V2 area into velocity. I will give the equation number 3. And we know that H is equal to P upon, that is pressure head and bottom head. H is nothing but pressure head and bottom head combined together is called as, okay, rho upon P upon rho G plus Z. And you know that the HL, that is head loss or energy loss, head loss energy, or F upon LD, F upon into V square upon 2G. I will give this equation number 5. Okay. Above every equation has dimension of length. Above every equation has dimension of length. It makes it possible to show the in the sketch for any pipe flow problem, that is the qualitative behavior of each term in these two equations. Okay, so here I write down the energy line, uh, total energy line, or energy grade line. Okay, so sometimes it is denoted by TL or sometimes it is denoted by EGL. Okay, whatever you write down. So it shows the EGL or TEL shows shows the the magnitude the magnitude of the Bernoulli sum of the Bernoulli sum of the Bernoulli sum, that is H plus V square upon 2G. This line this line this line is sketched by is sketched by starting from starting from its elevation known elevation at point upstream of upstream of reservoir, and sometimes it is called as, often it is referred as, uh, often a free surface of free surface of reservoir. It starts from the free surface of reservoir. Okay, so from the figure also you can come to know that it starts from the free surface of reservoir. TEL. Okay, है ना? So TEL is nothing but this term, this Zn rho upon V is nothing but H. You can write down this H plus V square pi 2G. Okay, so pressure head plus bottom head or position head is nothing but your H. That is here written. So that is nothing but your Bernoulli sum. That is nothing but your Bernoulli sum. That is H plus V square upon 2G. Okay, and that line is when sketched is called as total energy line. The friction losses are shown by if you don't understand any term, you can friction losses is shown by equation number 5. Equation number 5, that is HL is equal to FL upon D V square upon 2. Okay, to cause the because TEL to slope downward, slope downward linearly, 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 convert with with distance in the direction, in the direction of flow, of flow, of flow, and local losses, and that is given by local losses, and that is given by, can write down that HL is equal to, can write down K1 V1 minus V2 square divided by 2G, K2 V1 square 2G is equal to K3 V2 square 2G. Okay? So it is losses, energy losses at the different places. Okay? In which, in this equation, equation 3, 6, in which cross section at 1 and cross section at 2 are immediately, immediately, immediately upstream, upstream and downstream, and downstream. That is section 1 and 2. From sudden change in pipe geometry, from sudden change in cross section, you can say cross section, or sudden change in pipe geometry. So you can see here the pipe geometry is changing from here. This figure you can see here. This is the conduit pipe. Here geometry is different. Here geometry is different. So they are changing the geometry. So here you can see that geometry is different. Here geometry is changing. That's why we are incorporating that. Okay. So here, figure is very important. Huh? That's why I have drawn the figure first. Pipe geometry. And that creates the that creates the local that creates the local losses, that creates the local losses, that create the local losses, and are the result of, are the results of results of results of high effects of turbulence, or you can say that there is flow separation, flow separation, or you can say that the secondary flow. Secondary flow. So the losses occurs over a relatively short length of the pipes as a result of pipe expansion and contraction, vanes, walls, and other fittings. They are usually called minor losses. These are called as minor losses, and they are usually called as minor losses. They are usually called as minor losses because often they are small compared to the friction losses. This is not usually true. However, we will prefer to describe these losses as local rather than minor. So local losses, if you consider that is K1 is equal to at the start it is 1, K2 is equal to, you can find out 1 minus A1 upon A2 whole square, and K2, K3 is equal to A2 upon A1 minus 1 whole square. So all these losses, if you write down this equation 7, so you have to write down 7a, this is 7b, and this one is 7c. Okay, so these you can write down. That is nothing but from the figure you know that you can this uh, uh, if you write down on the your figure here. So this is at this point the losses K3, then losses K2, K3 at the junction. You can write down these are the losses. Okay, and then you can uh, where is it? Okay, you can incorporate that. Sorry for that. So you have to come over point. So that is TEL is nothing but TEL is nothing but right down total energy line over H plus V square by 2G, and where H is nothing but P upon rho G plus Z. So that is total energy line. Now we'll see the second is nothing but second concept, you know, the hydraulic hydraulic grade line, hydraulic grade line, hydraulic grade line. So write down the hydraulic grade line shows the hydraulic grade line shows the magnitude the magnitude the magnitude of piezometric head piezometric head H. Since H differs differs from the Bernoulli sum from the Bernoulli sum Bernoulli sum by by velocity head. So in while drawing or sketching the hydraulic grade line, that is HGL, so velocity head is not considered. Uh, on velocity head is nothing but V square upon 2G. That is the velocity head. So it is not considered. Therefore, the HGL is hydraulic grade line is parallel to TEL और EGL, that is total energy line, इसके पैरेलल रहेगा, but it lies because V square got 2G, we are not studying, but and lies below it, below it means below TEL by amount, because we are not considering V square by 2G, so by amount V square upon 2G. Since Z in the equation number 4 is is the is the elevation of pipe center line. Is the elevation of pipe center line. Center line from figure, we'll say 1. This is our first, we have drawn this figure. We can say that this is the figure 1, showing the hydraulic direct line and the total energy line. We can say this Z is nothing but center line of the pipe, that is Z from the data. Okay? That is shown on the figure. That is shown on our figure. Okay? So, and the pressure head. What is the pressure head? Pressure head generally P upon rho G or P upon gamma. P upon rho G is the vertical distance, vertical distance, vertical distance between HGL, hydraulic direct line, and pipe center line. From the center line pipe to the hydraulic direct line, that is the pressure head. Therefore, pressure in the pipe are positive and negative. Therefore, pressure in the pipe are positive or negative, you know, this depend on your HGL, huh? Negative. The HGL lies above and below the pipe center line. So अगर above है, it is above the pipe center line, the pressure head is positive, है ना? If above pipe center line, you can say here in the figure you can understand. This is the hydraulic direct line. This one. Change the color so that you can understand. Change the color. And this is the HGL line. Okay. This is the HGL line. That is hydraulic here. Okay. So here head is dropped due to the pipe cross section is changing here, है ना? यहाँ पर change हो रहा है. तो यहाँ पर what is the pressure head? It is nothing but the distance between the center of the pipe to the HGL, and that is nothing but your pressure head. That is P upon rho G. तो HGL अगर अबो है तो इट मे बी पॉजिटिव, और HGL अगर आपका इस तरह है, HGL बिलो है तो ये निगेटिव हो गया, नीचे आ गया। तो इट मे बी नेगेटिव और पॉजिटिव बेस्ड ऑन योर हाइड्रोलिक ग्रेड लाइन। अगर हाइड्रोलिक ग्रेड लाइन पाइप सेंटर के नीचे है तो इट मे बी नेगेटिव, और ऊपर है तो इट इज पॉजिटिव, इज इट इज पॉजिटिव। समझ में आया आपको? तो दैट्स व्हाई वी आर studying this hydraulic grade line and total energy line. Okay, so we will stop here, and next uh, lecture tomorrow we will solve some example. Today our workshop is starting, so I have to join the inaugural function. It may be started already, and you can also join. So thank you for joining today. Okay, we will continue the example on this Bernoulli's equation, so that we will understand how to solve the problems of fluid mechanics by using Bernoulli's equation. Okay, we'll take down later on. You all join the